Good day and welcome to this episode of differentiation. This is the third part, and we are going to be dealing with chain rule, which is also known as function of function. We are going to be dealing with the quotient rule also. So we are going to be diving to this quickly. For the chain rule, we have if y is sine 2x, then we are asked to look for the dy dx. I want us to understand that when we are dealing with chain rule, there will always be a complex function there. For example, you can see this is a complex function. Assuming they gave us sine x now, we just differentiate it and say it is cos x. But now we are having this complex function. So whenever you are having a complex function, you have to represent that by a particular letter, maybe u or something. So now I can say let u be 2x. So if I say let u be 2x, I will differentiate I will differentiate that u with respect to x here. Then since that u is already 2x here now, it will be y sine u because u is already 2x. So now I will have y is equals to sine u. So since u is already 2x, now I will differentiate this with respect to x, I will differentiate this with respect to u, and that's when the chain rules come in. So now if I have du dx now will be what? If you differentiate 2x, it's going to give you 2 because 2x raised to power 1, so 1 multiplied by 2, that's 2. Then 1 minus 1, that's 0. So x raised to power 0 is 1. Multiplied by 2 is still going to give you 2. We did create that in our differentiation 1 when we were doing the basics. So this is 2. Then sine u. If you are differentiating sine, it's going to give you cos, right? So I will divide du will be cos u. So now if you want to activate the chain rule, that will be dy dx equals to dy du, that's this, multiplied by du dx. Now this is the logic. Logic is that when du cancel du, you have your dy dx again. So that means this equation is balanced there. Now you now have to insert. So your dy dx now will be, what is your dy du, which is cos u. Then your du dx is what? 2. So that means your answer is what? 2 cos u. And we represented u as what? 2x before. So that u will be, I can put my u back now, which is 2x. So but in case you are in an obj and you need to work fast, maybe you don't want to solve through all of this, there's a very simple trick for it. This is y is equals to sine 2x. The rule is that you differentiate the complex number, which is 2x. When you differentiate 2x, you will get 2, right? So you bring that 2, you multiply it by differentiation of this sign, the function before the complex number. So if you differentiate sine, it's going to give you what? Cos. Then you write the remaining complex function in the front. You get my point? Now do what I'm saying. I differentiate this 2x, it gave me 2, right? Then I differentiated sine also, it gave me cos. Then I now come here and write the remaining function in the front. That is when it doesn't have power. So now let's go to the second one. You see how we go further on this. Now you have dy dx is equals to y 3x plus 5 raised to power 4. So now you can see that this is the complex part here, and that's what we're going to be representing by u. So I'll say let u equals to 3x plus 5. Now if u is equals to this, now that means my y will be what? U raised to power 4. Am I right? Because all this now is already u. So now we look for dy du, I will look for dy dx. See, this is with respect to u, this is with respect to x. So dy du used to be 4 times u raised to power 4 minus 1, which is 3. So that will be 4u raised to power 3. Then here we have du dx. So it's going to, we are going to differentiate this 3x. If you differentiate 3x, you have only the constant alone. So it will be 3. And if you are differentiating the constant, you don't have anything again. So now you apply the chain rule. Dy dx equals to dy dx. When you insert them, the dy du is this. 4 u raised to power 3 dot, and your du dx is 3. So now you can multiply. If you're having 12 u, you can insert your u there now. Where's your u? This, the one we represented here. So that will be 3x plus 5 raised to power what? 3. Now you have to pay attention here also. This is the answer for this. Now the short one is that, I said the complex number. You always note the complex number. So what is there now is that when you differentiate this, you are differentiating the complex number. When you differentiate this, you will have what? 3. Have you? So you are multiplying 3 with the power. You remember when you are doing differentiation, you should have always multiplied the coefficient of that function with the number. But now you are differentiating this and you are multiplying with the power. You differentiate this, you have 3. You multiply with the power, you have 12. Then what next? You write the function you differentiated at first. You write it normally. Then you now minus the power by 1 to give you your answer. So that is just the short. If you don't, maybe you are in case of OBJs and you need to work fast, just remember that differentiate the complex number, multiply it by the power, it's going to give you 12. Then after that, write that one you differentiated before there. Then you use your power minus 1. So that is all for that. Then we have quotient 2 here. We are dealing with quotient 2. We said find dy dx at x is equals to 5. Then if y is equals to this. Quotient 2 is when you have division or fraction that are complex also. So you make this u, you make this v according to the formula. So when you have your u and you have your v, you are going to be differentiating them with respect to whatever they are. This is what I'm saying. You have u is equals to x plus 2. You have v is equals to x minus 2. Then you are going to differentiate each of them with respect to what they are given. U with respect to x, v with respect to x. So that will be du dx for here, and that will be dv dx for here. Now, if you differentiate this, remember if you differentiate the constant, that one is gone already. So differentiate x to be 1, because x raised to power 1 multiplied by the 1 that is here, that's 1. Then 1 minus 1, the power, it will be 0. X raised to power 0 is 1. So it's 1 here. So the same thing here too, 1. Now, you now insert the formula. The formula is d dy dx for quotient 2 is v du dx minus u dv dx then over v square. So having known that, you just pick what you have gotten before. Your v is what? Your v is x minus 2. X minus 2 is and multiplied by du dx, which is 1. Then minus your u is what? X plus 2 multiplied by 1, because with dv dx is also 1. So divided by your v square, which is this x minus 2 square. And from there you can move on. So this multiplied by 1 will still give you x minus 2, then minus x plus 2, because you multiply 1, it's still going to be the same. So x minus 2 square. Now inside brackets here, inside brackets here. So if you open this minus is going to open this. Actually, if minus open this bracket, it's going to be a minus times minus times plus, which will give us minus. So we're having x minus 2 minus x then minus 2. So because of the bracket, the inside brackets, there's a subtraction in the middle. So it will be x minus 2 square, then x minus x is 0, then minus 2 minus 2, that will be minus 4 over x minus 2 squared. Let's take note, they said x at x is equals to 5. We shouldn't omit that. So if you are going to put x here, we want to get the final answer. It's going to be minus 4 over 5 minus 2 all square. So that will be minus 4 over 5 minus 2, that's 3. 3 raised to power 2, that's 9. So the final answer is 4 over 9. Final answer is minus 4 over 9. Let us move to the second part. Welcome to this one. This one is about definition of exponential logarithm. and definition of natural logarithm. So this ones are simple. You just have to flow along. Now, if we have exponential of f of x, I want you to note two things. If you have this, you can have y as a function of x. That is an explicit function. But if you have y and x in the same function and is equals to 0, that is implicit. There are videos on implicit on the channel, but they are for 200 level. But if you feel you want to check them, there's no problem. So now, if you are dealing with exponential, you are going to differentiate the power, then multiply it by the whole of that function. What am I saying? dy dx now will be what? d dx, it will be d dx of this f of x, then multiplied by the whole of everything, exponential f of x. Now, that's for that. So now let us come in. We are going to find the dy dx now. It's going to be dy dx. Remember what I said, you are differentiating the power, then you multiply it by the whole of this. So if you differentiate the power here, that will be 1, right? 1, then multiply it by the whole of this, that will be exponential x. So it's going to give you what? Exponential x. That is why they say if you differentiate exponential, it's still going to give exponential x. So that's the reason, that's the proof of it. So now here, let's come in, differentiate the power, then multiply it by the whole of the function. I'm differentiating this now, our dy dx will be what? 3 multiplied by 5. I'm differentiating this now. 3 multiplied by 5, that's 15. X raised to power 3 minus 1, that's 2. Then multiply it by the whole of it. That will be exponential 5x raised to power 3. As simple as that. So that's for exponential logarithm. For natural logarithm, which involves ln or logarithm of exponential, so we have ln function. Ln function is, if they say what is ln x, it's going to be 1 over x. Why? Because you are differentiating this, then you are going to multiply it by the inverse of the real function. Do you understand? So if you say you are having something like dy dx will be differentiation e dx of f of x, then multiplied by 1 over the f of x. Do we get? So that's the basic secret there. That's the basic secret there. So when you know this one, you are going to multiply it when you differentiate the power. You are going to multiply it by the whole of the function. But here, you are going to multiply it when you differentiate the complex parts in the front of the ln. You are going to multiply it by the inverse of that function you are dealing with. So now let's move here. Dy dx now for this place, we are having this, right? So we are differentiating this first, and that's 5 times 3, 15x raised to power 4. 15x raised to power 4, then multiplied by, it's going to be the inverse of this now. So we have 1 over 3x raised to power 5. So now we can now cut. We have 4x here, we have 5x here. So this we cancel this. Yes, we have only one x left here. So that is 15 over 3x, right? So now 3 here 1, say 3 here and 5. So that will be 5 over x. Now there is a shortcut for this one also. There is a shortcut for this, and this one is even more simpler. So the shortcut for it is that you just it's kind of funny, but you just take the power and you take the power, then the x here will be your denominator. That's all. We see when we solve the second one. So let's do the second one so that you have to clear your doubts. Let's do the second one. This differentiate this, right? So that would be 150 x raised to power 2, then multiplied by the inverse, which is 50x cubed. So here this will remain an x here, so that would be 150 over 50x. So now 50 here 1, 50 here will be 3, so that will be 3 over x. So you can see that it's that same 3 over x that you are getting. 5 over x, 3 over x. You can try it for other functions. 3 over x. So far as it's giving something, that's what you just have to, just have to be smart. So now for here also, you are differentiating this, right? And we multiply it by the inverse. Let's do it for these two. You have dy over dx will be equals to, differentiate this, is going to give us 1. So 1 multiplied by the inverse of that, that's 1 over x. This is the normal function for it. So it's going to give us what? 1 over x. So what is the rest? This x is raised to power 1, right? So that means it still applies to whatever we have been doing since. 1 over x, that's the answer. So this is the end for this differentiation 3. I'm going to be doing the next video, differentiation 4, very soon. Do well to like, share, subscribe, and comment. Thank you.